Our planet, Earth, feels solid beneath our feet. We build our homes on it. We walk on its surface every day. It seems stable, permanent, and unchanging. But honestly, this feeling of stability is just an illusion. The ground we stand on is not a single solid piece. Instead, it is broken into giant, interlocking puzzle pieces. These pieces are called tectonic plates. They are enormous slabs of rock that float on a layer of hot, molten material deep within the Earth. Think of them like giant crackers floating on a thick, hot soup. They are constantly on the move, but very, very slowly. This movement is so slow that we cannot feel it. The plates drift at about the same speed your fingernails grow. It might be just a few centimeters per year, but over millions and millions of years, this tiny movement adds up to enormous changes. Imagine you could watch a video of Earth sped up over millions of years. You would see a world in constant, dramatic motion. Continents would slide across the globe like pieces on a chessboard. Mountains would rise up from flat plains and then slowly erode away. Oceans would appear and disappear in the blink of a geological eye. This is the world of plate tectonics. It is a process that not only moves land masses, but also fundamentally builds the world. Without this movement, the surface of our planet would look very different. It might be a flat, water-covered world with no continents at all. This constant recycling of the Earth's crust is a unique feature. When an oceanic plate collides with a continental plate, the denser oceanic plate is forced to dive underneath. This process is called subduction. As the plate sinks back into the hot mantle, it melts. The melted rock can then rise to the surface, feeding volcanoes and creating new continental crust. This is how continents grow over time. It is a planetary renewal system that keeps the surface fresh and dynamic. The power of plate tectonics goes much deeper than just shaping landscapes. It is a planetary-scale thermostat, regulating Earth's climate over geological timescales. This might sound strange. How can moving rocks control the temperature of an entire planet? The answer lies in a delicate dance involving carbon, volcanoes, and the ocean floor. Carbon dioxide is a powerful greenhouse gas. Too much of it in the atmosphere, and the planet gets too hot. Too little, and it freezes over. Plate tectonics play the leading role in keeping this gas in perfect balance for life to flourish. Volcanoes, which are common at plate boundaries, release huge amounts of carbon dioxide into the atmosphere. This gas comes from the melting of rocks deep within the Earth. This process adds carbon to the air, which helps to keep our planet warm. But if this were the only process, Earth would eventually become a scorching hothouse, like the planet Venus. There must be a way to remove that carbon from the atmosphere, and there is. This is where the other half of the tectonic cycle comes into play. It is a slow but incredibly effective removal system that keeps the climate stable over millions of years. When it rains, carbon dioxide from the air dissolves in the water, forming a weak acid. This acid rain falls on the mountains and rocks that tectonics have pushed up. Let's journey back in time, not just thousands, but millions and billions of years. Imagine our planet not as the familiar map of continents we know today, but as a completely different world. The forces of plate tectonics have been the grand sculptors of this world, tirelessly working to shape and reshape its surface. They are like cosmic artists, using immense pressure and heat as their tools. The very ground beneath our feet is a testament to their slow, persistent work. Every mountain, every valley, and every coastline is a brushstroke in their magnificent planetary-scale masterpiece. When two tectonic plates carrying continents on their backs collide, something spectacular happens. Neither plate wants to give way. They are both thick and buoyant, like two massive styrofoam blocks being pushed together. So, instead of one sinking beneath the other, they crumple. The rock folds, buckles, and shatters under the immense strain. Over millions of years, this geological wrestling match pushes the land upwards, creating gigantic mountain ranges. The mighty Himalayas, home to Mount Everest, are a perfect example. They were born and are still growing because the Indian plate is crashing into the Eurasian plate. The continents we live on are not permanent fixtures. They're more like, giant rafts drifting across the surface of the planet on the slow-moving currents of the mantle below. If you could watch a time-lapse of Earth's history, you would see them dance across the globe. They join together to form immense supercontinents, like Pangaea, where all the land was once connected. Then, they break apart again, scattering across the planet in a slow, centuries-long continental ballet. This cycle of assembly and breakup has happened multiple times over our planet's long history. This movement has a huge impact on the evolution of life. When continents are joined together, land animals can roam freely across vast territories. We see this in the fossil record, where similar species are found in places that are now separated by thousands of kilometers of ocean, like South America and Africa. But when the continents break apart, populations of plants and animals become isolated from each other. These isolated groups then start to evolve along their own separate paths. Just as plate tectonics builds up the continents, it also carves out the vast basins that hold our oceans. This process often begins in the middle of a continent. Deep within the Earth, heat from the mantle can cause the continental crust to stretch and thin. It's kind of like pulling a piece of dough from both ends. It gets thinner and weaker in the middle. Eventually, the crust can crack and break apart. This creates a long, deep valley known as a rift valley. The Great Rift Valley in East Africa is a modern example of this process in action. It is a place where the African continent is slowly being torn apart. If this stretching and rifting continues for millions of years, the valley can sink below sea level. Water from the ocean floods in, creating a long, narrow sea. The Red Sea, which separates the Arabian Peninsula from Africa, is a perfect example of a young ocean basin being born. As the two pieces of land continue to move apart, a new type of crust begins to form in the gap between them. Molten rock from the mantle rises up and solidifies, creating fresh oceanic crust. The boundaries where tectonic plates meet are zones of intense geological activity. These are not quiet, peaceful borders. They are places of immense stress and conflict. The slow, steady movement of the plates builds up enormous pressure in the rocks along these fault lines. When that pressure becomes too great for the rocks to withstand, they suddenly break and slip. This abrupt release of energy sends powerful shock waves, or seismic waves, racing through the Earth's crust. We experience this sudden violent movement as an earthquake. These events can reshape the landscape in an instant, causing the ground to rip apart, triggering landslides, and even changing the course of rivers. Volcanoes are another dramatic consequence of plate interactions. They are essentially vents or openings in the Earth's surface that allow molten rock, ash, and gases to escape from deep within the planet. Most of the world's volcanoes are located along the edges of tectonic plates, particularly in subduction zones. As one plate sinks into the mantle, it melts, creating magma. The power of plate tectonics extends far beyond shaping mountains and moving continents. It plays a role that is perhaps even more critical for life. It acts as a planetary thermostat. Imagine trying to keep a house at a comfortable temperature for billions of years. You would need a very reliable heating and cooling system. For Earth, plate tectonics is that system. It regulates the planet's temperature over vast geological timescales, preventing it from getting stuck in a permanent ice age or turning into a runaway greenhouse. This regulation is achieved through a slow, elegant dance involving a very important chemical element, carbon. This process is what has kept Earth's climate stable enough for life to evolve and thrive. The key to this thermostat is carbon dioxide, a gas in our atmosphere. Carbon dioxide is a greenhouse gas, which means it traps heat from the sun. Think of it like a blanket for the planet. A thin blanket keeps you comfortably warm. Too thick a blanket, and you overheat. Too thin, and you freeze. The amount of carbon dioxide in the atmosphere determines how thick this planetary blanket is. The story of carbon removal continues in the world's rivers and oceans. The chemical weathering of mountains releases minerals like calcium and magnesium, which are then carried by streams and rivers down to the sea. Along with these minerals, the rivers also carry the carbon that was pulled from the atmosphere, now dissolved in the water. Once in the ocean, a new set of players takes over. Marine life. Tiny organisms like plankton and corals use the dissolved calcium and carbon to build their hard shells and skeletons. They are essentially creating tiny, intricate structures out of calcium carbonate. When these countless tiny organisms die, their shells and skeletons do not just disappear. They sink slowly through the water column, creating a constant, gentle shower of marine snow. This material settles on the ocean floor, building up layer upon layer over thousands and millions of years. The immense pressure from the overlying water and sediment eventually compacts these layers. In this way, carbon that was once a heat-trapping gas in the atmosphere becomes locked away as a solid part of the Earth's crust. This process is a one-way ticket for carbon, taking it out of circulation for a very long time. This entire system, known as the geological carbon cycle, is a beautiful example of a self-regulating feedback loop. It works to counteract any major climate swings. Imagine the Earth starts to get too cold. Ice sheets would expand and sea levels would drop. This would reduce the amount of rainfall and slow down the chemical weathering of rocks. However, volcanoes driven by tectonics would continue to pump carbon dioxide into the atmosphere. With less carbon being removed, the concentration of this greenhouse gas would slowly build up, warming the planet and melting the ice. Now imagine the opposite scenario. The Earth starts to get too hot. A warmer world would lead to more evaporation from the oceans and therefore more rainfall. This delicate balance is the secret to Earth's long-term habitability. It has not kept the climate perfectly constant. Our planet has gone through ice ages and warm periods, but it has kept the global temperature within a range that allows liquid water to exist on the surface for billions of years. Liquid water is the one ingredient that all life as we know it depends on. To truly appreciate the gift of plate tectonics, we need only look at our planetary neighbors. Let's start with Venus, a planet often called Earth's twin. It's similar in size, mass, and composition to our own world. From a distance, it seems like it should have had a similar story. Yet Venus is a hellscape. Its surface temperature is hot enough to melt lead, a scorching 465 degrees Celsius. The atmospheric pressure at its surface is over 90 times that of Earth's. Thick, swirling clouds of sulfuric acid completely hide its surface from view. So what went so terribly wrong with our supposed twin? The answer seems to lie in large part with its lack of plate tectonics. Venus does not have a system of moving plates like Earth does. Its crust appears to be a single solid lid. Without the constant motion and recycling of plate tectonics, Venus has no planetary thermostat to regulate its climate. There is no subduction to pull carbon-rich rocks back into the planet's interior. Volcanoes on Venus likely pumped enormous amounts of carbon dioxide into its atmosphere over billions of years, just as they did on Earth. Now let's travel in the other direction to our other rocky neighbor, Mars. The red planet tells a different but equally cautionary tale. Mars is a small, cold and dry world with a very thin atmosphere. Its surface is a desert of reddish dust, pockmarked by craters and home to giant, extinct volcanoes. Yet we have compelling evidence that Mars was not always like this. Billions of years ago, it was a much warmer and wetter planet. We see the clear signs of ancient riverbeds, deltas, and even vast ocean basins carved into its surface. So, what happened to Mars? Why did it turn from a potentially habitable world into a frozen desert? The answer, once again, seems to be linked to the loss of plate tectonics. Mars is much smaller than Earth, about half the diameter. A smaller planet cools down much faster. Early in its history, Mars likely had a hot core and a convecting mantle, just like Earth. But as its internal heat engine cooled and sputtered out, its geological activity ground to a halt. The planet's internal dynamo shut down, its magnetic field vanished, and its tectonics died. Looking at Mars today is, well, like looking at a geological ghost. Its massive volcanoes are these silent monuments to a more dynamic era. Olympus Mons, for example, is the largest volcano in the solar system. It's actually 3 times the height of Mount Everest. Its sheer size suggests it sat over a stationary hotspot for an incredibly long time. On Earth, a moving tectonic plate would have drifted over the hotspot, creating a chain of smaller volcanoes. The immense size of Olympus Mons is, ironically, evidence of a lack of plate movement. It's a giant tombstone marking the place where Martian geology took its last breath. The thin Martian atmosphere we see today is, well, less than 1% as dense as Earth's. It's mostly carbon dioxide, but there's just not enough of it to create a significant greenhouse effect to warm the planet. The planet's thermostat is, you could say, permanently broken, stuck in the off position. This comparison between Earth, Venus, and Mars really paints a very clear picture. Earth exists in a Goldilocks zone of geology. Venus is too geologically active in a catastrophic stagnant lid way, leading to a runaway greenhouse effect. Mars is just too geologically dead, leading to a frozen thin atmosphere. Our journey through the solar system has shown us just how special Earth is. The dead worlds of Venus and Mars highlight the critical role of plate tectonics. But our solar system is really just one among billions in the Milky Way galaxy. For the first time in human history, we have the technology to look beyond our immediate neighborhood. We can now search for planets orbiting other stars. These distant worlds are called exoplanets. The hunt for these exoplanets is, honestly, one of the most exciting fields in modern astronomy. We're not just looking for any planet, we're looking for another Earth, a world that might have the right conditions for life. The discovery of the first exoplanet orbiting a sun-like star in 1995 opened the floodgates. Since then, powerful telescopes like NASA's Kepler Space Telescope and now the James Webb Space Telescope have found thousands of them. We've discovered a stunning variety of worlds we never imagined. There are hot Jupiters, gas giants orbiting scorching hot close to their stars. There are mini Neptunes and rocky worlds of all sizes. This cosmic census has revealed that planets are, honestly, incredibly common in our galaxy. It seems that most stars have at least one planet, meaning there are potentially trillions of planets out there in the universe. Finding these planets is the first step. The next much harder step is to figure out what they are like. Most exoplanets are too far away and too small to see directly. We detect them indirectly, often by watching for the tiny dip in a star's light as a planet passes in front of it. This is called the transit method. From this tiny wink of starlight, we can calculate the planet's size and its orbit. How can we possibly tell if a planet hundreds of light years away has active plate tectonics? We cannot send a rover there. We cannot see its mountains or continents directly. Instead, we have to become planetary detectives. One of the most promising methods is to study the planet's atmosphere. When a planet transits its star, a tiny amount of starlight passes through its atmosphere. By analyzing this light, we can look for the chemical fingerprints or spectra of different gases. This technique is, honestly, like a cosmic barcode scanner for atmospheres. The presence of certain gases in a planet's atmosphere could be a powerful hint of active geology. For example, a significant amount of carbon dioxide is expected on a rocky planet. But if we also see gases like sulfur dioxide, it could be a strong indicator of active volcanism. On Earth, volcanoes are the primary source of this gas. Finding both together would suggest a world where volcanoes are actively replenishing the atmosphere, a key function of plate tectonics. This would be a tantalizing sign that the planet has a geological engine that is still running, releasing gases from its interior and potentially regulating its climate. Among the thousands of exoplanets discovered, one class has emerged as particularly intriguing: the so-called super-Earths. These are rocky planets that are more massive and larger than Earth, but smaller than icy giants like Neptune. They can be up to twice Earth's size and, well, 10 times its mass. There are no super-Earths in our own solar system, so their discovery has opened up a whole new area of planetary science. Scientists are now wondering if these larger, rockier worlds might actually be even better candidates for long-term habitability and plate tectonics than planets exactly like our own. The reason for this optimism comes down to planetary physics. A more massive planet would have a hotter interior. It would contain more radioactive elements decaying in its core and mantle, which is the primary source of a planet's internal heat. This extra heat means a super-Earth's geological engine would be more powerful and could run for much longer than a smaller planet's. While Mars cooled quickly and its tectonics died, a super-Earth might keep its mantle churning and its plates moving for many billions of years. The search is on for a super-Earth in the habitable zone of its star, one that we can study with the James Webb Space Telescope. Finding such a world and detecting the telltale signs of a tectonically regulated atmosphere would be a monumental discovery. We began this journey by looking at the ground beneath our feet, a surface that feels solid and permanent. Yet we've discovered that this stability is, honestly, a grand illusion. Our planet is alive, not just with biological life, but with geological life. Its surface is a mosaic of colossal plates in constant graceful motion. This movement, known as plate tectonics, is the planet's heartbeat. It's a force that has sculpted our world, building majestic mountains and carving out the vast ocean basins. It's the unseen artist behind the diverse and dramatic landscapes that make our world so visually stunning and varied. Our planet functions like a grand, intricate symphony. The movement of the plates is the slow, powerful rhythm section. The eruption of volcanoes and the shaking of earthquakes are the dramatic brass and percussion. The weathering of mountains and the flow of rivers are the sweeping strings. And the result of this symphony is a world that is not just a static rock in space, but a dynamic, interconnected system. Plate tectonics is the conductor of this symphony, ensuring all the parts work together to create a harmonious and life-sustaining planet. It is the hidden power that makes Earth a truly living world. Our exploration of our solar system neighbors, Venus and Mars, serves as a powerful and honestly kind of sobering lesson. These worlds highlight what happens when the geological symphony falls silent or plays a discordant tune. Venus, our so-called twin, is a cautionary tale of a runaway furnace. Without the cooling mechanism of subduction to bury carbon, its atmosphere grew thicker and hotter until it became a toxic, crushing hellscape. Mars, the frozen red desert, tells the opposite story. It's a planet that lost its inner fire. Being smaller, it cooled down too quickly. Its geological heartbeat faded, its volcanoes fell silent, and its tectonic activity ceased. These two worlds suggest that plate tectonics might be a great filter for habitability in the universe. The concept of the Great Filter proposes that there are certain critical steps an aspiring living world must pass, and many planets may fail along the way. Our quest for knowledge now extends far beyond our solar system, to the countless exoplanets orbiting distant stars. With powerful tools like the James Webb Space Telescope, we are peering into the atmospheres of these alien worlds for the first time. We're no longer just counting planets. We're beginning to characterize them. We are searching for the telltale chemical fingerprints of a world that is geologically alive. The discovery of gases like sulfur dioxide could hint at active volcanism, while the subtle changes in a planet's light as it rotates could suggest a mix of continents and oceans, the hallmarks of a tectonic system. Ultimately, the question of whether plate tectonics is the secret ingredient for life remains one of the most profound questions in science. Answering this question will require decades of future observations, new and more powerful telescopes, and perhaps even missions that can one day travel to these nearby star systems. The answer will tell us a great deal about our own origins and our place in the cosmos. As we stand on the solid ground of our planet and look up at the night sky, we are filled with a new appreciation for the hidden power churning deep beneath our feet. The silent, slow dance of the continents is not just a geological curiosity. It is the engine of our world's vitality. It is the force that moderates our climate, enriches our world, and provides the stable stage for life's 4-billion-year drama. The restless skin of our planet is what makes it a living, breathing home. And as we continue our search, we are looking not just for a pale blue dot, but for a world with a geological heartbeat just like our own.